No matter what direction we look, we see the same structural pattern. Stars in galaxies, galaxies forming groups of galaxies, and groups of galaxies forming clusters of groups of galaxies. Now in our local group of galaxies, there's about 19 galaxies. Andromeda and Milky Way, our home galaxy, are the biggest two in our local group. Galaxies come in a variety of shapes. One of the more popular shapes is a spiral. Our home galaxy, the Milky Way, is a spiral galaxy. A variation on the spiral galaxy is a barred spiral. You have a straight section going through the core and then the spiral arms coming off of that. Elliptical galaxies are more or less spherical or oblong galaxies. Irregular galaxies have become irregular apparently through gravitational interactions with another galaxy. The image here shows two galaxies colliding. Those collisions are interesting because remember how far it is to our nearest neighbor star? About 4 light years. So even though when you look at the picture of the galaxy it looks like things are tightly packed, you've actually got a lot of empty space between the stars. So two galaxies can collide, and for the most part there's not a whole lot of head-on collisions between stars. For the most part the stars simply pass by each other. A lot of empty space in a galaxy. However, the gravitational interactions will distort the shape of the galaxy and you'll end up with a very ragged, irregular looking galaxy. Back in the old days, the small telescopes didn't have a whole lot of resolution, and so you had very blurry images. And the old astronomers tended to classify a blurry object that moved as a comet. If it was a blurry object and it didn't move, then it was a nebula. So there's an awful lot of different things out there that were lumped in the general category of nebulas. By Herschel's time, the resolution of telescopes had improved a bit to where they could start making out some of the details of those nebula. And Herschel studied what were known as the spiral nebula and speculated that these spiral nebulas might be large clusters of stars, that is to say, really spiral galaxies. He couldn't prove it, however. Actual proof that these spiral nebulas were spiral galaxies had to wait till the 20th century. Hubble's work with the best telescopes of the day, the Mount Wilson 100-inch and the Mount Palomar 200-inch, definitely showed that these spiral nebulae were made up of stars. Our home galaxy, the Milky Way, is a fairly large spiral galaxy, about 100,000 light years across from edge to edge. Now, Pluto, remember, is about 39.4 astronomical units from the Sun. If you run through the calculations, that works out to be about 5.5 light hours. So our solar system's about 11 light hours across. And so you realize that if the galaxy is 100,000 light years across, our solar system is just a tiny speck in the Milky Way galaxy.
Given the appearance of spiral galaxies, it's not surprising that they all rotate. That is, they spin on their axis. Spiral galaxies vary in size from about 1 billion on up to a few 100 billion stars. They all seem to have the same sort of structure. In the center, you have a globular-shaped nucleus tightly packed with stars. Surrounding that, you've got a flat galactic disk made up of spiral arms of dust and gas. Then, surrounding that, galactic halo of globular clusters of old stars. We are about 2/3 the way out on one of the spiral arms.
The galactic disk is made up of clusters that we call galactic or open clusters of stars. And the number of stars in each of these clusters varies from, maybe a dozen on up to maybe 1,000 stars or so. These stars that make up the galactic disk are called population 1 stars. They're thought to be second-generation stars. And the reason we think they're second-generation stars is they contain small but measurable amounts of heavy elements. That is, elements beyond iron in the periodic table. Remember how we think these heavy elements are generated. Supernova explosions, create heavy elements. That debris flies through space until it runs into a cloud of gas and dust, contaminating that cloud of gas and dust. When that cloud collapses to make stars, your typical galactic nebula, those stars are now contaminated with the debris from a previous supernova explosion. They've got heavy elements in them. Our sun is thought to be a second-generation star. Debris from supernova explosions flying through space isn't just something that happened billions of years ago. It's an ongoing phenomena. And we can recognize this phenomena through ionization of the Earth's upper atmosphere. Victor Hess and others investigated what they call cosmic rays. Something was coming from outside the Earth, slamming into the Earth's upper atmosphere, causing the formation of the ionosphere. One of the factors there is, of course, the sun, the solar wind. But even at night, we see high-speed particles slamming into the Earth's upper atmosphere. Particles that are going much faster than the solar wind particles. In fact, some of these supernova debris particles are traveling at a reasonable fraction of the speed of light. 70, 80, some cases even 90% of the speed of light. The globular clusters forming a halo around our galaxy are thought to be the first stars that formed in the region of our galaxy. These are called population 2 stars. They're all old stars. We think of these as the first generation stars in our neighborhood. Think they're first generation stars because when you do the chemical analysis on them, you find that they don't have the heavy elements of your population 1 stars. These stars apparently were formed from a cloud of gas and dust that was essentially pure hydrogen and helium without contamination from previous supernova explosions. Remember, Hubble studied galaxies and discovered that the farther away the galaxy was, the bigger its Doppler red shift. The bigger the Doppler red shift, the faster it's moving away from us. So, more distant galaxies are moving away from us at higher speeds. The implication of this is that the universe itself is expanding. Hubble's discovery is one of the cornerstones of the beginnings of the Big Bang Theory. Up until the beginning of the 20th century, the only way astronomers could look at the universe was through their telescopes using visible light. Well, in the 20th century, we've discovered radio, X-rays, gamma rays, infrared rays. We've discovered a lot of different ways of looking at the universe. Things look different at different wavelengths. The picture there is a picture of our galaxy at different wavelengths, and it does look significantly different at different wavelengths. In some cases, there are very bright objects at one wavelength that are invisible at other wavelengths. One of the more interesting discoveries made with radio telescopes was that of quasars, quasi-stellar radio sources. They're quasi-stellar in the sense that the real size of the quasar is smaller than the resolution limit of the radio telescope. They have extremely large redshifts. They were the most redshifted and therefore the most distant objects ever discovered at that time. Now, in order for you to see a very distant object, it's got to be very bright. And the calculation said these things were extraordinarily bright. 100 to 1,000 times the brightness of a galaxy. Well, remember, a galaxy can have billions of stars in it. So how can you have a single object brighter than 1,000 billion stars or more? Particularly, when they did further calculations, they realized that this single object had to be maybe the size of our solar system. And our solar system, remember, is just a tiny speck compared to a galaxy. The eventual answer was the only thing we could figure out that could power something like that would be a supermassive black hole. If you got a supermassive black hole, you have an enormous gravitational field, can pull in a lot of matter very quickly, compress that matter, heat it up, the matter radiates before it disappears beyond the event horizon. You can have almost unlimited brightness. In order to see a black hole, it's got to be feeding. That is, pulling in and consuming surrounding matter. So these quasars, in order to be very, very bright, have got to be pulling in, consuming enormous amounts of material. So where are you going to find that amount of material to feed on? Well, the logical answer is the core of a galaxy. Current observations suggest that most, if not all, galaxies have a supermassive black hole at their center. The thing that distinguishes a quasar from the other galaxy cores is that in a quasar you've got large amounts of material falling inward, and so you have a very bright object. For galaxies like our Milky Way, our supermassive black hole is basically on a diet. Only a little bit of material is falling into it, and so it's glowing very dimly. In 1916, Albert Einstein expanded special relativity into general relativity. One of the implications of general relativity is that the universe must be either expanding or contracting. A static universe would not be stable. However, in 1916, there was no evidence to suggest that the universe was anything but static. Hubble didn't discover the expanding universe until 1929. So Einstein added into general relativity an anti-gravity term called the cosmological constant. Once Hubble discovered the universe was expanding, Einstein felt that the cosmological constant was no longer needed and removed it from general relativity and called it his greatest blunder ever. However, in more recent times, other physicists have realized that the way the universe is expanding, we need something like the cosmological constant. We need an anti-gravity term of some sort to explain the expansion of the universe. So the cosmological constant's back in. 1929, Hubble discovers that the universe is expanding with his studies of redshifts of galaxies. And this is really the beginnings of the idea of the Big Bang Theory. The idea is, if the universe is expanding, then it's bigger than it used to be. And so if you run the clock backwards, the universe shrinks and shrinks and shrinks, and logically eventually gets down to a single point. Now, properties of the universe. As you compress anything, it gets hotter and hotter and hotter. So we can plug in our basic laws of physics and calculate what's happening in the universe as we run the clock backwards to the beginning. Also, you run the clock forward, the universe expands and it cools. So the universe is a much cooler place than it used to be. One of the important factors in evaluating the correctness of a scientific theory is how good are its predictions. The Big Bang Theory has made a number of continuing successful predictions. And one of the most famous of its predictions was that there should be a cosmic background radiation, that the universe should glow, and it should glow at a wavelength that corresponds to its current temperature. The predictions were the temperature should be fairly low. The wavelength should be in the microwave region. And this cosmic background radiation was discovered by two people who were not looking for it. Finnis and Wilson were working for Bell Labs researching background noise that might interfere with the development of satellite communications. They found this noise that didn't seem to have any source. No matter where they pointed their antenna, the intensity of the noise was the same. They had discovered the cosmic background radiation predicted by the Big Bang Theory. When they measured the wavelength, you discover the universe has cooled down to about 3 Kelvin. The Big Bang Theory predicted that the cosmic background radiation should be very uniform, with just some very, very tiny ripples in intensity. In 1992, analysis of the Cosmic Background Explorer satellite's data showed that this is exactly what was happening. The cosmic background radiation was very uniform with just some tiny variations in intensity. Just what the cosmic background was predicted to be by the Big Bang Theory. One of the things the Big Bang Theory gives you is a way of estimating the age of the universe. And the calculation looks pretty simple. Distance divided by speed. If we know distances to galaxies, and we know the speed with which they're moving, then we just run the clock backwards and we come up with a number for how much time it's taken for everything to get to where it is. Of course, the problem with this is it's not quite as simple as all that. And of course, there's a problem of speed. The problem, however, is, has the speed been constant? And the assumption is that the speed has not been constant. But once you take all these complications into account, the best current estimate is the age of the universe is somewhere in the ballpark of around 14 billion years old. Now, one of the things you love to do in science is cross-check your results. And so is there some way that's independent of the Big Bang Theory that we can have that'll give us some cross-check, some validation of that number? And there's several of them. A couple of them are, well, theory of stellar evolution and decay of radioactive isotopes. In theory of stellar evolution, what we're really looking at is nuclear physics. How fast does nuclear fusion take place? Because the faster the fusion takes place, the quicker the stars burn out. And remember, according to our theory of stellar evolution, our sun is a second-generation star. And furthermore, if we look for the first-generation stars and find the oldest stars we can find, we find that they look like they're, somewhere in the neighborhood of about 8 billion years old. So theory of stellar evolution implies that the universe has got to be something more than 8 billion years old. Now, a nice thing about this is that theory of stellar evolution goes back to basic nuclear physics, fusion. It does not depend on whether the Big Bang Theory is right or wrong. It's independent. Likewise, decay of radioactive isotopes. We take long-lived isotopes like uranium and look at how long they've been decaying. And this is how we figured out the age of the Earth. Well, we figured out the age of the Earth's got to be somewhere in the neighborhood of about 4.5 billion. Well, this automatically tells you that the universe itself has got to be greater than 4.5 billion years old. Once again, independent technique. Rate of radioactive decay does not depend on whether the Big Bang Theory is right or wrong. So it's independent. So both rate of radioactive decay and theory of stellar evolution tell us that 14 billion is a reasonable number for the age of the universe. The universe is currently expanding. One big question is, will the universe continue to expand forever? The answer is, depends. Depends on whether or not you've got enough gravity to stop the expansion. If you do not have enough gravity to stop the expansion, then the universe will continue to expand forever, and we have what's called an open universe. If there is enough gravity, the expansion will slow and stop. In that case, we've got a closed universe. Determining whether the universe is open or closed turns out to be more difficult than you might think. Because in order to figure out how much gravity you've got to add up all the matter that you can see. What's the average density of matter in this section of the universe? The problem there is we can see the matter that's glowing, the stars, etc. But what about the matter that's not glowing? And this is the dark matter problem. If it's not glowing, how do you measure it? It turns out that we can use observations of galaxies to make some estimates of how much matter there is in the galaxy that's not glowing. And then the next question is, okay, what is this dark matter? Is it just cold hydrogen and helium that's not glowing brightly? Or is it something more exotic like neutrinos? It's a whole nother question. And finally, we've got the energy problem. And that is, remember Einstein's cosmological constant? Well, it turns out that a thing called dark energy can have the properties that Einstein postulated for his cosmological constant. That is, an anti-gravity expansion term. The trick is, how much dark energy is there, and how do we go about measuring it? Another big question is, are we alone? Is the Earth the only place in the universe with life, and are we humans the only technology-building intelligent life in the universe? Well, we don't know for sure, but we can make some assumptions and see where those assumptions lead us. One is, when we look at the sky, we discover that the sun is kind of a middle-of-the-road main sequence star. It's a pretty common type of star. And if stars like our sun have got planets, then there's got to be billions and billions and billions of planets out there. When we look at the sky, we discover that the sun is kind of a middle-of-the-road main sequence star. It is a pretty common type of star, and if stars like our sun have got planets, then there have got to be trillions of planets out there. So what evidence do we have that there's billions of planets out there, planets orbiting other stars? Well, when we look at our ideas about how our solar system formed, there isn't anything in there that says that this is a unique or unusual process. So we think that planets are probably pretty common. Maybe not around every star, but probably you've got some sort of planets orbiting most stars. The problem with taking pictures of those planets, however, is, first off, planets are small and dim compared to stars. You're going to have a big telescope to collect enough light to see the planet. And second, remember the resolution problem. When you look at a star, you see a blurry blob that's bigger than the star itself. That blurry blob will cover and engulf most of the planets in orbit around that star. Using the Hubble Space Telescope, scientists have made an artificial eclipse of Beta Pictoris and several other close stars. And what they find is that when you block out the photosphere of these stars, then you have a dimly glowing disk or ring of comet-like material surrounding those stars. Looks a lot like we'd expect our Oort cloud or Kuiper comet belt to look like if we were viewing our solar system from a great distance. If you've got a big planet, a Jupiter-sized planet, and it's in close orbit around its star, the gravitational interaction of that planet will tug the star a little bit as it goes around. So as it comes around towards us, it'll tug the star towards us. As it goes around to the other side, it'll tug the star away from us. We can detect very, very tiny Doppler shift changes in the radiation from that star. And those tiny Doppler shift changes allow us to calculate orbits for the planets. If there are billions of planets out there, what about life? Well, just because you got a planet doesn't automatically mean you've got life. But if you've got billions of planets, statistically you'd think that the conditions would be right somewhere besides just on the Earth for life to be possible. In order for life to be possible, well, you got to have the right temperature range. It's got to be the right distance from a nice stable star. Got to have the right mixture of elements. After all, there's a limit to the chemistry you can do with just hydrogen and helium. And of course, an atmosphere would be nice. Might not be absolutely necessary, however. Even if life turned out to be fairly common throughout the universe, it's unlikely that technology-building intelligent civilizations are common. If you think of the Earth as our one example of life, think of all the species on the Earth, all the species that have ever lived on the Earth. How many of them build technology? Spaceships, radio telescopes, etc. Only one, us. So it could be that technological civilizations are very rare throughout the universe. So if we're going to communicate with these civilizations, we may have a long wait because speed of light. The signal can't travel any faster than the speed of light. If they are 10,000 light years away from us, their signal to us takes 10,000 years. Our answer back to them takes another 10,000 years. A 20,000 year loop for the conversation. A lot can happen in 20,000 years. And for one thing, they can stop waiting for the phone to ring and turn off their radio telescopes. Another thing is, think of the changes that have occurred in human civilization in the last 10,000 years. By the time the signal gets back to them, their civilization may not even exist anymore.